So, welcome back. This is Dr. Ron Prafer from Western New England University. We've been going over a brief tutorial on various components of medicinal chemistry to help you guys for your tests in the future and as well as the present. We've already spoken about acids and bases, but now let's go into more of the meat of the calculations. Now, this is not a heavy calculation. However, there is log button on your calculator that you will be required to understand. So, firstly, let's go over what is an acid. Well, okay. I'm going to go back to firstly, let's go over. So firstly, let's ask ourselves, what is pH? Now again, you've probably learned this in high school chemistry. It's just been a while. pH is negative log of H+. That's what P actually stands for, negative log. Now remember, it's referring to the solution and not the functional group. Common error. Functional group, we talk about pKa. Solution, we talk about pH. What it does is sort of lets us know how much free H+ is floating around the solution. So if we have a pH of 0.1 molar H+, what that means is it has a pH of 1. So remember, pH is equal to negative log of 0.1, so therefore you have a pH of 1. So what is a pH if you have a solution of 0.0001 molar H+? Very simple. Punch in your calculator, you should get a pH of 4. So that's what pH is. What is pKa, however? This is where it is. Well, if you look at it simple, pKa is equal to the negative log, hence the P of Ka. What does Ka stand for? This is where it gets a little bit more complex. Again, this is high school, but just a refresher, and I apologize if it comes across as belittling. The Ka is the H+ concentration times the A- concentration over HA concentration. And this is a property of the functional group. It's affected by some various factors, sterics and electronics, but the rule is simple. The stronger the acid, the lower the pK value. The weaker the acid, the higher the pK value. Now, we spent a lot of time in earlier tutorials going over how a base becomes an acid. If you do not get that, go back to, I believe it would be part 3. So, let's move forward. You've probably heard about the Henderson-Hasselbalch and Henderson-Hasselbalch equation, which is pH is equal to pK plus log of unprotonated over protonated. This is the formula that you will need to memorize. There is actually 4 versions of it. Only memorize this one. And here's the way. pH is equal to pK plus log of up. U over P, up. You get that in your head. Do not talk about any other equation, okay? We can use this to calculate pH. We can calculate the ratio between the salt and its acid form. We can calculate the pK, the percent ionization. But the key thing is, I do not want you to use any equation that uses the word ionized and unionized. It's going to confuse you. I've been doing this long enough to know where students falter. All you want to know is protonated versus unprotonated. So in this form here, you have the acid that's protonated on the left. On the right, it becomes unprotonated. It's a base. On the bottom, we have and it's an acid. And this is where you have to remember this. This is an acid. This is a base. The acid is protonated. The base is unprotonated. So just remember the protonated over unprotonated. Who cares? Ionized versus unionized. That's understanding how it's water soluble. But whether or not, for this math, it's just protonated over unprotonated. So if we take a look at a molecule that has a pK of 4.5. Firstly, what's the functional group that has this pK value? It's the carboxylic acid. Falls directly in that range. So the first question I have is, will this be primarily protonated or unprotonated in your urine, which happens to have a pH of, hypothetically, 8.9? What about in the stomach if it has a pK of 2.1? So we can do this just general qualitatively, which we did numerous times in earlier parts, but we can also do it quantitatively. So let's just do it first qualitatively. we know that this molecule has a functional group, which happens to be carboxylic acid, that has a pK of 4.5. So what will happen at pH 5.9? So again, go this step by step. Imagine you're the molecule and you're at pH 4.5. That means because your pK is 4.5 and you're now in a solution of 4.5, you would be a 50-50 mixture of your protonated form as drawn and the unprotonated form, the O-. Remember, acids are going to be neutral or minus. Bases, neutral or positive. So, here we go. We're at pH 4.5, we're at a 50-50 mixture. If I go up to pH 5.9, from pH 4.5 up to 5.9, what's happening? There's more OH minus floating around to abstract that proton. Therefore, it's going to be more O minus. So, compare those two. Is 5.9 more basic or less basic compared to 4.5? Let's look at 2.1, your stomach. Again, you start off at 4.5. At 4.5, this molecule is 50% this, 50% minus. If I go down to pH 2.1, there's much more H plus floating around, so therefore it'll exist preferentially like this. So it'll be neutral. But you already know the answer. But let's prove it mathematically. Let's give 100% proof. And that's the cool thing about the Henderson-Hasselbalch. You should be able to match them up. At any moment in time, you can actually calculate it out to a T. So pH is equal to pK plus log of up. So we have a pH of 5.9. We have a pK of 4.5 plus log of up. So 1.4 is equal to log of up. Therefore, 25.1 is equal to the concentration of unprotonated over concentration of protonated. Therefore, and remember, you should stop the video recording, double check on your calculator, get this answer here. There should be no calculator flaw at this point, but it happens a lot. So therefore, is the denominator or the numerator bigger if you have a value of 25.1? The numerator must be bigger. This must be 25.1 over 1. So therefore, it exists more unprotonated, which is exactly what we said 2 slides ago. How about we try the other one? Let's take the same drug molecule and put it in your stomach as a pH of 2.1. So pH is equal to pK plus log of up. 2.1 is the pH. The pK is 4.5 plus log of unprotonated over protonated. Negative 2.4 is equal to log of unprotonated over protonated. Again, use your calculator and you should get 0.00398 is equal to the concentration of unprotonated over protonated. Therefore, the denominator must be bigger. Therefore, there's more protonated. And again, go back a couple of minutes and you'll see that's exactly what we stated. Let's look at another example. There can be thousands of examples. We're not going to go over a whole 1,000, but there are a lot. The drug molecule below contains a function group somewhere that has a pKa of 3.1 and another that has a pK of 9.2. Firstly, where are they and what will they be protonated or unprotonated at physiological pH? So, now if you don't know how to do this, you must go back to part 3 when I talked about bases. As drawn, there is nowhere where there's a pKa of 3.1 or 9.2. Okay? But there's a functional group that could possess that pK value once it's protonated. If I protonate here, this H, put an H off of this nitrogen, it will have a pK of 3.1 because now it's an acid. If I put a proton off this nitrogen, it has a pK of, it's now an acid, it has a pK of 9.2. This is an amide. You ignore amides. Please never touch an amide. I've seen it so many times. Amides are neutral. So will these two function groups be more protonated or unprotonated in physiological pH? How about in the stomach? So let's go straight to let's do quantitative and qualitative. Well, let's look at this. So at pH 3.1, and the aniline must be that one there, have the pK of 3.1. This tertiary amine must have the pK of 9.2. Will there be primarily protonated or unprotonated at physiological pHs? Well, let's look at the 3.1. Well, firstly, physiological pH is 7.4. So I'm looking at this. Right now, this does not have a pK value. If I put a proton off here, this has a pK of 3.1, meaning at pH 3.1, it's a 50-50 mixture of this molecule and the protonated form. At pH 2, 1, 0, it has more of the protonated form because there's more H plus floating around. At pH 7.4, there's more OH minus around to take off that extra H. So therefore, it would be much more basic in comparison, therefore it exists preferentially like this. But in the stomach, comparing 3.1 to 2.1, this is much more acidic, therefore more H plus is around. But let's prove it again. pH is equal to pK plus log of up. 7.4 for the pH, 3.1 for the pKa. So 4.3 is equal to log of up. 19,953. That must mean that the numerator is bigger than the denominator, therefore more unprotonated. If we look at the other pH, the 2.1, the stomach, again, same thing. Now we get to -1 is equal to log of unprotonated over protonated. Therefore, 0.1 is equal to unprotonated over protonated. Therefore, the denominator must be bigger. Therefore, there's more protonated. The other values were 9.2 and 7.4. Again, we'll just go straight to the quantitative versus qualitative. And you should have much more protonated versus unprotonated. And again, with the stomach, now we're really going to huge difference in when you're comparing 9.2 to here was 7.4. The other one's going to be 9.2 down to 2.1. Huge difference. And again, you end up with 0.000, a whole bunch, unprotonated versus protonated. So there's much more protonated. But what percentage is actually going to be protonated? What percentage will be unprotonated? Well, you're actually only one step away. And this is the most amazing part. People get to this point and they freak out. You're actually only one step away. So let's just take an example, the previous one. 9.2 compared to 7.4. We got to this. What percentage is actually unprotonated and what percentage is protonated? Well, we know that this is the case. So therefore, for every molecule, so that we can actually write it this way, in fact. So therefore, for every molecule of protonated, there's 0.0158 molecules of unprotonated. Yes, we can have less than a molecule, but just bear with me for a moment here. So therefore, you have 0.0158 molecules of unprotonated and 1 of protonated. So total, there's 1.0158. So remember, I'm talking about percentage. Well, 0.0158 over 1.0158 times 100 equals 1.56 unprotonated, 98.4% protonated. That's it. Let's look at the other example. We had we were comparing pK of 4.2 and a pH of 5.9. We did this whole beautiful calculation, just like that. We knew that there's going to be more unprotonated versus protonated, but by how much? Same equation. Well, there we got the 25.1 is equal unprotonated over protonated, meaning for every molecule of protonated, there's 25.1 molecules of unprotonated. So therefore, there's a total of 26.1 molecules in the whole slurry of things. 25.1 of those is the unprotonated form. So 25.1 over 26.1 times 100 equals 96.2% unprotonated and 3.8% protonated. That's it. And year after year I'm stunned that is where people have problems. So I recommend if you didn't get that, just go back, try it yourself on your own calculator. Just stop at the beginning of the page, like stop right about here. what percent, and then just do the math yourself. You know the answer is going to come anyways, and get it over and over again. And you can do it with any combination. You pick a pK and a pH and you get it every single time. And that way, if you cannot mathematically comprehend it, or you can't figure out by looking at it, whether it be more potent or unpotent, you can mathematically figure out and get it that way there. I would advise to first figure it out, looking at part 2 and 3 that I presented earlier, but you should be able to do it that way there. Okay, so come back and join me for a more in-depth look at using pH and pK on other components.